So let's try a simple example, and then we'll have you guys do one. Something really simple. Let's say you have just a tank of water here. Okay, so I'm going to draw the surface of the water. So here's water, and here's air. And I have a laser beam, maybe like a laser pointer, and I'm going to shoot this, shine this laser pointer in this direction, and I draw the normal to the surface, and that laser beam is going to bend when it goes through the water. Okay, so I'll call again that theta 1, the angle between the normal and the light ray, and this is theta 2. Okay. Let's say theta 1 is equal to, I don't know, 30 degrees. We know N1 is equal to 1.0029. The index of, so I'm calling this 1 and this 2, basically. N2 is the index of refraction of water, so that's 1.33. So go ahead and try it. See if you can use Snell's law, N1 sine theta 1. Equal to N2 sine theta 2. See if you can solve for theta 2. Solve for the the angle that the laser beam makes in the water. What'd you get? 22 degrees? Theta 2 is 22 degrees? Okay. So it just comes from solving for sine of theta 2 is N1 sine theta 1 over N2, and then you just take the arc sine or the inverse sine of that result, right? And you should have 22 degrees, okay? So we see that this angle was 30 degrees, and it becomes smaller when it goes into the water, okay? Well, we could have, so let's just recap. We went from a low index of refraction, air is only 1.0029, to a higher index of refraction, and we saw that the light ray gets bent toward the normal. And you could show that's a general result. What about this? Let's say we have a beam of light traveling upward through glass into water. Now you might say, well, how in the world can that happen? Well, I don't know. Maybe you have a glass, okay, some glass container, and you have a light down here, and you're shining light up into the glass, and then it goes into the water that it's containing. Or maybe like a light at the bottom of a pool, okay? If you have a light that's enclosed in a glass fixture, and it's shining upward into a pool of water, it starts down here, and it's going up here. Now, the subscripts, you got to be a little bit careful here. Theta 2 is referring to the index or the angle in glass. Theta 1 is the angle in water, and theta 1 is the thing we're trying to find. Okay, so it makes an angle of 20 degrees with the normal while in the glass. At what angle does it emerge when it goes into the water? And again, the diagram is not to scale. Indices are 1.33 for water, 1.46 for glass. Let's try it out, see what we get. Oh, say that one more time. If it's perpendicular, so if it goes through, you're talking about like you have a surface here, and the light ray goes straight down, then it's not going to refract, right? Because theta 1 is equal to 0, and theta 2 is equal to 0. Yeah, that's right. And you kind of saw that in the demo, because you saw that as those light rays moved farther away from, that one was sort of straight on, right? That one bent kind of like that, and the farther away you moved, the more bending there was from the normal, right? Okay, so the question is, what happens if the light ray stays the same direction, but the interface changes? Well, if your surface changes angle, then your normal is going to change angle too. So that's going to affect. Yeah, well, it's going to depend. It's going to vary back and forth. But the key idea here is not the direction of the light ray, but the direction with respect to that normal. And if that normal changes, then the refraction angle is going to change as well. Oh, well, it depends on okay. so you're talking, it depends on the source. Okay, now let's say you have a source of light that's emitting light in all directions. Okay, well, it could emit, I mean, even way out here, right? I mean, I could go arbitrarily far away, and Snell's law is still going to apply. If I have an angle that's very big, I have that's theta 1, and then theta 2 is going to be something like that, and I can calculate what theta 2 is. Now you have a limit where it's getting so far away that the angle is 0, right? But as long as there's a non 90 degree theta 1 here, and we're going from air into water, there's going to be some refraction, and we can calculate that. Now if we're going the opposite direction, that's a different story. We'll get to that in just a second. Okay. But what do we got here? We get, answer number 5, 22.1 degrees. It's not, which is just a pure coincidence. It's the same numbers we got last time. It's not every refraction is 22 degrees. But okay, we get the same. We go through the same type of reasoning. We find that in this case, what happened? We went from an index of refraction that was large to an index of refraction that was smaller. And what happened to the light ray? The angle got bigger, right? So the light ray got bent away from the normal, right? Got bent away from the normal. So here's a case where we have a light ray. So we went from a lower index to higher. Light ray is bent toward the normal, toward that perpendicular line. In the other case, we had a light ray going from a higher, and again, this is an exaggerated picture, but we have a higher N and a lower N here. If you go from a higher to a lower N, you have light ray bent away from the normal.